Hi, welcome to the Calculus 1 lecture series. And we are starting, this is the unit number 1 for the Calculus 1. And in this unit, we're going to start with the limits concept. And then we're going to, from the limits, take a look how the derivatives, was defined. So the lecture number 1, even before we talk about the limits, we're going to take a look, some very brief discussion about the tangent line, secant line, and some velocity problems here, how they're going to relate it to later, when we talk about the limits and derivatives here. Okay, so the lecture number 1, we're going to talk about the sections, and we just basically introduce the tangent line, secant line, and the velocity problems. So we have the the average velocity, and we have instantaneous velocity. What are those things here? All right. Okay, so now let's go to our lecture notes here. And let me see here. Okay, so this is our lecture notes. Okay, so the first things here, what we want to do is let's define what is the secant lines here. Okay, so the secant line, first, let me just, draw the graph first, and then we can write it out, the definitions here. All right, so here I have curves here. Okay, so this is, we call this the f of x here, or you can say this is f of x equal to the y's here. So what is the secant line? So the secant lines, that means if I get the 2 points, like if I get this point, I get these points here, right? So the secant line, if I get the 2 points, that means this is the line, and going through these 2 points here. So I hope I can draw this line good. Okay, so this is the line, the green one, and the passing through these 2 points. And of course, I did not do very good job in the very difficult to draw line, using the, okay, so here. So this is what we call this the secant line, okay? So that's basically, you have 2 points on the graph, and then these 2 points you go through, we call this the secant lines here. So the secant lines here, that means, the secant line is a line, right? Is the line through the point P and point Q. You can call the one is P and the one is Q. And so like in here, so that's what we call the this is. So if I call this is point P here, and this is point Q here, right? So the point P, we said the coordinates here, this is AB. And the point Q here, the coordinates here is CDs here. Okay, so we said if the Q has coordinates, okay, CD, and P has coordinates, what? AB here, okay? Then the slope of the tangent line, secant line, slope of this secant line. So the secant line is like you have like, the 2 points, right? So if this is the, okay, so take a look here. If this coordinate is C, right? So that means here is C, and then what is the height here? I'm sorry, this is the A, then this is the B, and then this is the C, this is the D, right? So in order to find the slope of this secant lines, we know the slope is rise over runs, correct? So the rise here, we rise from the B to D. So the rise over run, so will be the D minus B, and what? And over what? C minus A, C here, right? So this is how do we define the slope of the secant lines here, okay? And now the next thing is here, let's take a look. What is the tangent lines here? The tangent lines here, so let me see if I want to find the tangent lines here. So what is the tangent line? Tangent line is a line only touch this graph at one point. So from here, this red one, oh, I do this one pretty good. So this red lines here, this is what? This is my tangent lines here. And as you can see, right? So that's what is the tangent line. So let's try to write down the, okay, so the tangent line. So what is the tangent line? It's the line touch the graph of a function, okay, at what? At one point here. Okay, so now the reason why we want to introduce the tangent line. So let's here, if you take those green lines here, as you can see, if you push this point CD, get closer and closer. So if you push this point, for example, go over here, right? So if you push the CD, go over here. So what happens here? Your secant line going to get closer and closer to the what tangent lines, right? So when the C get closer to the ace here, then my secant line will getting closer and closer, right? So because if I push this CD, if I put this point here, look what is my, see here, right? This green one, see here. So this green one, so this secant line is way closer than the original secant line to become my tangent lines here, right? So the reason why we want to introduce these ones here, so that's why we know is when the, so when the C getting closer, okay, getting closer to ace here, then the secant line, what here? Secant line will become closer to the tangent line, right? So the secant line, finally, when the C become A, then the secant line will become to the tangent line. So that means that I can use the slope of the secant line to estimate the slope of the tangent line, right? Because the tangent line is only touched one point. And I know in order to get the slope, I need to have 2 points, right? Because of the rise over run. So how do I get the slope of the tangent lines here? I can use the slope of the secant line to estimate. So if this point getting closer and closer, right, to the original point here. Okay, so let's take a look at some examples here. So like in here, they say, let the P15 be a point at the graph 6x minus x squared, and let qx be also on the graph. Find the slope of the secant line PQ. Give the x value of the q. Okay, so right now my P points here is what? My P point is 1, 5, and my Q is what? My Q points here is given here, right? So it's given the x and the f of x. Okay, so now let's take a look. Let's say the first ones here, if I put the Q started at the 3s, right? So that means that in here, the 3, so if you plug the 3 in here, what I have 6 times 3 is 18 minus 3 squared. So this is 9, right? So this is my Q point, 3 and 9, right? Okay, so this is my point of Q. Just like in here, I started with initially the point Q, so this is 9. So now you can find the slope. Slope is rise over run, so it's 9 over what? 9 minus what? Start with the piece, right? 9 minus 5 over, then the x is what, where? 3 minus 1 here, right? Because it's in here, my point P is 1, 5. So this is my first point, 3, 9 to the 1, 5. What is the slope, right? So we got this one here. I got this is 2. Okay, so now I getting closer because this one's here, right? So take a look here. This point is 1. So now I push my x just like the c values here. I push it to get closer. So let's take a look. If this is 2, what happens here? So what is my point Q? If you put this is 2, 6 times 2 is 12. 12 minus 2 squared is 8, right? So I'm sorry here. So when x equal to 2, then my values here is what? Is 8, right? So now I can have my slope here will just be a minus 5. So this is my second point, 2, 8, right? So you use 2, 8 and 1, 5. So it's a minus 5 and 2 minus 1. So what is here? This one's here, so 3 here. Okay, so now I have 1.5. So this is my another point, 1.5. Then you put the 1.5 to the f of x. So it's 6 times 1.5 minus 1.5 to the square. What I'm having here, 6.75. So this is my another point, 6.75 here. Now you plug in and see what is the slope. So this is 6.75 minus 5. Then this is 1 minus 5 minus 1, right? So what I have here, I have a 3.5 here. Okay, now I'm choosing another one very close to 1. I'm choosing 1.01. Okay, so this is 1.01. So you put a 1.01 to the f of x, and what you have here, if you put it into your calculator or you just do a quick calculation by yourself, you can get a 5.0399. Okay, now let's take a look at what is the slope here. 0.0399 minus 5. Now what is here? This is 1.01 minus 1, right? So what is this one here? 3.99. Okay, so now I know, seems like when I push, did you see here? So when you push this x very close to here, then you got some value getting closer and closer. So it's probably I'm going to reach what? Reach the force here. All right. So that's why, use your answer in the table to guess the slope of the tangent line, the P. So I know when I push this point getting closer and closer here, right? So my slope becoming closer and closer to 4. So I'm guessing, so the slope is probably equal to 4 based on these tables here. Now they want to find the equation of the tangent lines here. Okay, so the equation of the tangent line. So I'm going to use the slope and so this is what you learn in the algebra. You need to use the slope and the 1-point formula to find the lines, right? So to find the line. So the slope and the 1-point formulas, if you remember, it will be what? Will be y minus y1 is equal to the slope x minus x1 here. And in here, since we estimate the slope going to be equal to 2 because of based on this table. So now I can say my slope, so my tangent line at the point 1,5 will be what? Will be 1 minus 5 is equal to what? 4 times x minus 1 here, right? Okay, so now if you simplify it a little bit, you can say this y equal to the 4x plus 1 here. So that will be our tangent lines here. Okay, and now before, let's see how do we use these ones here. So let's take a look at what is we call this the average velocities and the instantaneous velocity. This is just the application about what we just learned here, right? Okay, so in here we say we suppose, okay, we have an object moving along a okay, and if f of x represents the distance the object is located, okay, then we know the slope of the secant line between P and Q is the average velocity. And the slope of the tangent line at the point Q, at point the P is the instantaneous velocity. Okay, so the first thing is here, let's take a look here. So here, so we said a function f of x represent the distance between the object is located here, right? So we typically call this is a position function. Okay, that means where is your objects, right? Then the second line, so like in here, it's a kind of, you say, hey, from the Dallas to Austin, right? So you driving there. So what is the average velocity? Is kind of like a speed, right? So you travel, what is the distance between these 2 points? How long is take it, right? That's what we call this, the slope, right? So that means you have the position function, and you have time to travel and the distance. Then the instantaneous here, that means at one specific moment, right? So if you look how fast your car is going, that's what we call this instantaneous, we call that is instantaneous velocities here. Okay, so let's take a look at the problems here. Okay, so we said f of x, the f of x is x squared plus 3x is the distance in feet in a race car, and traveling from the starting point and after the, hold on here. Okay, starting point after x seconds. How far has the race traveled? The 2 seconds? After 4 seconds? What is the average velocities of the time interval between 2 and 4? What is the instantaneous the velocity at x equal to 2? See here. Okay, so now let's take a look. So we know this is a position functions, correct? So this is our position function. That's what is the distance, how long it travels here. Okay, so now when the x equal to 2, right? So when x equal to 2, you plug in f of the 2. So this is 2 to the square plus 2 times 3. So this will be what? This will be the 10 feet, right? Now when x equal to 4, then how fast I'm traveling? 4, see here, this is 4 to the square plus 3 times 4. Okay, so this is 28 feet, see here, right? Okay, so now they said, what is the average, right? So in here, I'm looking for what is the average velocity between the time interval x2 into x to 4 here. Okay, so the average velocities we know will be what is what we call the slope of the secants, right? So the first we say, okay, we travel, so from f of the 4, f of the 2, then the 4 minus 2 seconds here. So you travel the 28 minus 10 in 2 seconds. So what is that? So that will be 9 feet per second. Okay, so this will be the 9 feet per second here. Then they say, what is the instantaneous velocities of the x equal to 2? So in here, we are finding the instantaneous velocity. That means I'm finding the tangent line. But in here, I don't know how to do that yet. That's what is like in our next topic, the next few sections, we're going to talk about how to find the derivative. So I will say, okay, I'm going to estimate. So this is my x, this is my f of x, and this is, I want to find, this is the slope of the secant. Okay, so let's start, all right? So because from the 2 to 4s, right? Okay, so I want to find instantaneous when the x equal to what? X equal to 2 here. Okay, so let's start approaching that. So the first, let's start with 3. So you put the f of x 3's here, you will get what here? 18. Now let's take a look at the slope here. The slope will be the 18 because I'm going to choose, right? So I use 2, so it's 10, right? So minus 10, and it's 3 minus 2. So this one is 8. Now I say, okay, let's get a little bit closer to 2. I said 2.5. Then you put a 2.5 to the f of x. It's 2.5 squared plus 3 times 2.5. You will get a 13.75 here. Okay, so you do the same thing. So you say 13.75 minus 10, and do the 2.5 minus 2. So what are you going to get close to? 7.5. All right, so we say, okay, let's choose a few more points. It's 2.1. You put a 2.1 to the f of x, so it's 2.1 square plus 3 times 2.1. What you have here is 10.71 here. Okay, so let's find the slope. So it's 10.71 minus 10, and divided by 2.1 minus 2. What is here? It's 7.1. Okay, so now I choose another one. 2.01. Okay, so you plug it into the function and you will get this is 10.0701. Very close. So now you can say that this is 10.0701 minus 10. Then you have 2.01 minus 2. So this is 7.01. So I guess from the tables, right? So from the table, you can conclude what is the value they were going to approach to. You probably approach to what? The slope of the tangent will approach to what? Approach to 7 here, right? So the slope of the tangent will approach to 7 here. So I know that's why the instantaneous velocity will be equal to what? 7 feet per second here, because you kind of you will do a table, you can see how fast it approach, which number it approach to. Of course, like later, we're going to show you how do we do that by using the calculus methods here, all right? Okay, so let's take a look at the next here. They say let f of mx plus b is a linear position function. So they want to ask the sometime, always, or never, the average velocity of the xx from the P to Q is the same of the instantaneous velocity. So what is this answers here? So this one's here is always. Why is always here, right? So because we know this is a slope intercept form. So that means it will be lines here. This is y equal to the mx plus b. So if you choose any 2 points here, right? So the 2 points, so the slope of this ones here is equal to, or you just choose 1 point here, then the, still, so it's the same, right? So as we said here, the reason why we say this is because the tangent line, and all the secant line are the same line. Right? So the other same line, this line is mx plus what? This one is mx plus b here. Okay? And so now let's take a look at the problem number 4 here. Okay, so the number 4 here is the distance that runner is from the starting point to the t seconds given in the tables here. Okay, so now let's take a look. See here, find the average velocity in the interval from the 1, 4, 1, 3, 1, 2, and 0, 1. So this one is very similar. So we just do the same things here. We say, okay, here, let's try to take a look here. So this is the interval. All right, so now here, this is the average velocity. Okay, so let's take a look from the interval 1, 4, right? So from 1 to 4. So when the t is 4 seconds, what is the meters here? Is 24. So this will be 24 minus when t is equal to 1, right? So what is t equal to 1 is 4, right? Now what is the bottom here? This is 4 minus 1. You get that? Okay, so this will be the 20 over 3. So this is 6.67. Okay, so meter per second. Let's take a look at the second interval. Second interval is 1, 3. And then when the x t equal to 3 is what? It's here, right? So it's 16. And t equal to 1 still is 4. So it's 4. Then this is 3 minus 1. So what is here? This is 12 over 2. So what I have is 6 meters per second. Now let's take a look at the other interval. This is 1, 2, see here. So if I get it from the 2, 2 is what? 2 is 9, 1 is 4. So it's 9 minus 4. So this is 2 minus 1. So this is 5 over 1. This is the 5 ms here. Now, in here, this is 0, 1. Okay, so when the x equal to 1 is 4, x equal to 0 is 0, right? So t equal to 0. So this is 1 minus 0. So this is the 4 meters per second here. Okay, so now in here, okay, so the next thing is here. So let's say, hey, let's try to estimate the velocity, the instantaneous velocity at t equal to 1. Okay, so I'm going to estimate the instantaneous velocity of t equal to 1. So I know these intervals and this interval, they give us the average velocities of what? 5 and 4. And they both have the 1s, right? So we can estimate instantaneously velocity at t equal to 1, and will be, we just like kind of the average these two. Okay, so it's 5 plus 4 divided by 2. So it will give me the 4.5 meters per second here. All right. And so for this ones here, it's kind of like we can try to, because this is a close one. So here, then you say, how about here, the 1, 3? Yeah, you can do that, but it's kind of like, you want to get closer and closer to the 1 you try to do, right? So it's 1, 2, and 0, 1. Probably is the closest value to the t equal to 1 here. All right. And I think that's it for the first lectures here. So in this lecture, we covered 2 very important concepts, right? So the first concept is the slope of the secant lines here, right? The secant line, so that means they touch the curve at 2 points. So then that's easy to find the slope of 2 points. We all know that from the algebra. Then we also want to find the slope of the tangent lines. So we know the slope of the tangent line. The tangent line is the functions, right? They only touch what? It's the function they only touch the graph once here, right? So that's why let's, if they only touch the graph like in here, right? They touch the graph of once. So how do I do that? I need to estimate. How do I estimate? I just push the secant line, right? At this point. Oh, okay. So basically, I just elect this point, getting closer and closer to my what point? To my P points here. All right. Then that is how can I, use the secant line slope, try to approach the tangent lines here. So that's the one of the key concepts. And then the next key concept in this lecture will tell you that, one of the application is the velocity problem. So we have an average velocity and we have instantaneous velocity. So instantaneous velocity is very similar, like you have the slope of that tangent line at your position functions. All right. And then the average velocity is the slope of the secant line of your position function. So you will have the 2 points there. Okay, that's it. And I hope our first lecture give you a good understanding about the tangent line and the secant line, because later when we derive the limits and the derivative, we definitely will go back to revisit this again. All right, so it's nice to talk to you, and you have a good day, and I will talk to you in our next lectures here. All right, bye.